Right, so I don't know if you're as excited about this news from LIGO as I am, but this is a really big deal, and we need to understand what gravitational waves are before we can really talk about what they found in the experiment. So I'm going to start by making an analogy to electric charge. So it's like this. You've got an electric charge here, and it's positive, and so field is coming out from it. And I'm a big fan, I think a lot of physics teachers are in my class, of saying the electric field goes for all distance. Like this electric field goes forever. But you wonder about what happens if this charge were to move, right? Because then does the new electric field go for forever? And so I'm going to try to draw a picture of what happens if this charge, which is right now creating an electric field that's causing a force on this charge right here. Let's name these guys. Here's Q1 and here's Q2. Q2 is sitting here just feeling a force. So maybe it's a small positive test charge feeling a force because of this charge. But you know, if I take this charge and I move it straight up, then the field around this charge needs to change because this one needs to get the information that this one has moved. And does it happen instantaneously or not? There are a lot of people who will believe that that happens instantaneously. But that doesn't explain delays like satellite phone discussions, or if there's a satellite link in the news, you know, there's always that lag. There's something like, don't you think the people who have the money to make these programs would have fixed that by now if it were physically possible? I think so as well. So I'm going to show you what happens if this positive charge moves upward. It's very interesting what happens is the field that has already gone long ago remains. And so that field is still there. And it's not that the field itself is propagating, but it's that information that the field has changed propagates. So let's say that the charge was here in the center, and it was there at some time ago. So it was there, let's define this distance as, that's the radius of that circle, let's call it all the way in there. And that's going to be the speed of light times the time ago that it moved. So t sub m, that's the time that it's spent moving. And so that is a distance, because we've got velocity times time. So I'm going to say that the charge during that time has moved up to here. So here's the charge right now, a positive charge, and we've got field coming out from it, and the field coming out from it has changed its angle because of the fact that the charge has moved. And those lines connect like this. So the field is skewed by the presence of that new velocity. And there's a break right here. This is a weird thing. And that happened because of the acceleration. So there's probably something really interesting going on at those instants right there when the charge got flicked and began to move at a constant velocity that direction. Let's see. Why is this not velocity? Oh, that's interesting. So the distance that it has gone can't be the same as the radius of this circle because the charge can't move as fast as the speed of light. If the charge were moving at the speed of light, then these waves would pile up on each other, and you'd have like a sonic boom, but for electricity. You really don't want to mess with that. So here's what I need you to believe. I need you to believe that if you were over here, if you were this charge right here, and you see that you sense, what I mean is you sense the field from the old charge where it was, then after some amount of time, you will sense the new field. So we could draw a little graph of what that looks like, because at some time, this is going to be, let's say, the electric field in the x direction. And let's define x right here. The electric field in the x direction is going to be doing what? Let's see, I think it's going to be getting a little bit weaker as this moves up. So all of a sudden, you're going to see a steady field, and then all of a sudden, it will begin decreasing. And it's probably going to be some kind of smooth thing right there. But this is the time that it takes, time for information about movement to get to Q2. And that has to do with how far apart these are. If these were farther apart, that would have been a longer time. But that has to do with the speed of light at which the information about the motion of the charge gets there. That's when that time happens. So I'm going to erase this. I hope you can save a picture of that, or maybe you've sketched it, because I'm about to talk about gravity as I promised. We're going to expect similar results for gravity because, well, you can talk about the electric force, and then you've got your Kc and your Q1 and your Q2, and you're dividing it by r squared. But you can say that that looks kind of like the gravitational force. Not that they are about the same, because that number is very different, but that they look really, really similar. This is the separation distance, this is the quantities of mass, those are the quantities of charge. So we expect mass here, charge here. We expect really similar behavior, these two equations, and we found it yesterday. That's what's really exciting. The problem is we can't find gravitational waves very easily because gravity stuff, that is massy stuff, doesn't tend to accelerate very much. By its very nature, if I just write down Newton's second law and solve it for acceleration, you will see, hopefully you will believe me, that the more mass you have, the less acceleration you're going to get. So the only time we're ever going to see enough acceleration when there's a big enough gravitational field to actually measure the change in the gravitational field is if, for instance, two rips in space-time were actually to collide into each other. Yes, I'm talking about black holes. So it's like imagine these black holes, which are an abomination already if you don't believe in Einstein's theory. And there are people who don't, and I guess I'm talking to you right now if you don't. There's this disturbance. Oh, the problem is, here's the problem. The problem is, I'm talking about forces over here, and I'm not really talking about forces in this video. I'm talking about the structure of space and time itself. That was what Einstein's idea of, well, general relativity, which leads to black holes, that's what it was. It was that space itself is disturbed by the presence of a mass. And I need you to think of that sheet, and you can find these videos readily online if you see a visualization of gravity as the curvature of space-time, right? There's this guy who's got a sheet of maybe it's spandex, right? And he throws an orange into the middle of it. You throw a little marble and the marble goes woo, and it can do orbits and stuff. It's a great visualization tool, but I want you to think of that sheet. Now, if the orange moves from place to place, and give the sheet a little bit more mass, so the wave takes a little bit longer. Here's a wave, and I have to get a chain out because it has enough mass to show you a wave. It goes like that, right? And the only reason you can see it, and it's not ultra fast, is because this has so much mass. So give that sheet more mass. Make it like gooey. And move the orange from place to place on the sheet. Can you imagine? That ripple will take some time to propagate out. That ripple is the information about the motion of the orange going from one place to another. And that is a gravitational wave. So I want to back up a little bit and talk about what a wave is. It's just a disturbance in a medium that propagates. And gravity? Well, I suppose a gravity wave is a disturbance in the size and shape of space itself that propagates. Because I believe these things, I believe that a black hole looks like this. It's the bending, and ultimately in a black hole, the rupture of space-time, where this sheet is bent and pulled so much that it tears, and we don't know what's going on in there. That's a black hole. But any mass bends the fabric of space and time itself. So if I shake this back and forth, then over here there'll be a ripple, a shaking. And that was observed yesterday for the first time ever. So I want you to imagine these black holes. We gotta have these black holes in space, and they're orbiting each other, right? This is a big, big mass, and in a sufficiently large force, the force is what gets you. Right, and I'm going to go through their details in another video, but the force is sufficient to cause such an enormous acceleration of these masses as they orbit each other. Now I want you to think, oh okay, so let's do it this direction. I want you to think of these black holes orbiting each other, and let's say they're the same mass. They orbit their own center of mass. It's not like one's fixed and the other one's dancing like this. It's not like this one's fixed and the other one's dancing like this. It's like they orbit each other and the center of mass. So I want you to think of them like celebrities, right? These black holes, oh yeah, they're popular. And they would orbit each other all day long unless the entourage. So you got Taylor Swift over here and Kanye West, right? And they got an entourage, and their entourages, as they get closer, their entourages begin to interfere with each other. Like these guys over here with Kanye, and these guys over here with Taylor. Well, they're having a little bit of trouble because they're bumping into each other, and they may be posturing a little bit. Shh, watch it now. Shh. And they bump into each other, and there's friction, and they lose their velocity. They lose that kinetic energy that they've got because they're bumping into each other, and that kinetic energy is then released as heat, and that stuff gets hotter and hotter, and those entourages get smashed into each other more and more, and they're slowing down. And they're slowing down, and what do I mean by they're slowing down? I don't actually mean they're slowing down. I mean they're colliding with each other, and they're losing their tangential velocity. And so they're actually spiraling into one another and speeding up as their potential energy, this gravitational potential energy between them, is turned into more kinetic energy. So by this strange process of bumping into each other and slowing, it activates the gravitational potential energy. I guess I mean that it frees that, it liberates it, and allows it to turn into more kinetic energy, so slowing is speeding up. Are you with me so far? So they're going faster and faster as they're spiraling into each other. These are black holes, mind you! Rips in space-time. They are colliding into each other, and we can see that. Because they cause these ripples in space-time, and these ripples can be detected. So if you have a detector, and I'll go into more detail on this in another video, but if you have a detector and it says like space-time, this is my favorite kind of detector. I'm going to be super vague about this right now. If you have a detector that measures space-time, then you're sitting here on Earth, it almost always measures a flat line, because space-time is pretty darn steady right here. So if you, though, are listening to vibrations in space-time with an interference meter or an interferometer, then you would see that shaking, that ripple. Now it has to be a very, very sensitive machine, and you can't have anybody walking near it. And it has to be enormously big, like 4 kilometers, for instance, this direction, and another 4 kilometers this direction. But if you had such a thing, then you could see this. You could see those 2 black holes. Dead stars, rips in space-time, spiraling into one another, and you would see the frequency of that ripple increase. So you would see this. It would be first slow, and then faster. And then so fast that the holes actually merge. Can you imagine? Not with Kanye because he's married. But actual black holes, 2 of them orbiting, entourages colliding, dragging, speeding up, suddenly you just have 1 black hole. So it gets actually more exciting than this. It's not just slow and then fast, it's also slow and then fast and huge. These disturbances, as they get faster and faster, become more significant until the black holes are 1. I guess that means that the disturbance is all within the event horizon of the single black hole. The 2 event horizons have completely merged. And then you get the standard thing that you see in physics. You get a little ring down. This is a relaxing mass. It's just a mass on a spring. This is a mass on a spring right here. But this is really interesting because you've got this envelope here of increasing frequency and increasing amplitude. Not a normal sort of thing, and we call it a chirp. And I like to call this the most expensive musical production in the history of mankind, because what was it, $40 billion? And 40 billion, some enormous number of money, amount of money, and 40 years of research that went into this project, and we heard the chirp that you can readily hear online. So please listen to that chirp and marvel in how expensive it was to find. But know this, the chirp demonstrates experimental evidence of black holes colliding with one another. So I guess that's right. And the chirp demonstrates that the speed of light exists. This happened a very long time ago. These black holes collided. And the chirp demonstrates that gravity is not a force. I can go into this more in the next video. The chirp demonstrates that the distance between 2 objects is affected by what's happening somewhere else. That space and time itself can ripple and can change. If you're having trouble understanding that, that's okay. I do too. Good luck. I think so as well. So I'm going to show you what happens if this positive charge moves upward. It's very interesting what happens is the field that has already gone long ago remains. And so that field is still there. And it's not that the field itself is propagating, but it's that information that the field has changed propagates. So this one has moved. And does it happen instantaneously or not? There are a lot of people who will believe that that happens instantaneously. But that doesn't explain delays like satellite phone discussions, or if there's a satellite link in the news, you know, there's always that lag. There's something like, don't you think the people who have the money to make these programs would have fixed that by now if it were physically possible? And I'm a big fan, I think a lot of physics teachers are, in my class, of saying the electric field goes for all distance. Like this electric field goes forever. But you wonder about what happens if this charge were to move, right? Because then does the new electric field go for forever? And so I'm going to try to draw a picture of what happens if this charge, which is right now creating an electric field that's causing a force on this charge right here. Let's name these guys. Here's Q1 and here's Q2. Q2 is sitting here just feeling a force. So maybe it's a small positive test charge, feeling a force because of this charge. But you know, if I take this charge and I move it straight up, then the field around this charge needs to change because this one needs to get the information that... Right, so I don't know if you're as excited about this news from LIGO as I am, but this is a really big deal and we need to understand what gravitational waves are before we can really talk about what they found in the experiment. So I'm going to start by making an analogy to electric charge. So it's like this, you've got an electric charge here, and it's positive, and so field is coming out from